So our first speaker is Matthew England. He's a Sensia Professor of Climate Dynamics at the University of New South Wales. His research explores global scale ocean circulation and its influence on regional climate, including large-scale oceanography, ocean modeling, and climate processes. He has a particular focus in the Southern Hemisphere. He's a fellow of the Australian Academy of Science. He's a fellow of the American Geophysical Union. He has served on science and engineering councils of 2 prime ministers and is recipient of many awards, including the Land and Water Australia Eureka Prize, the Royal Society of Victoria Research Medal. He has served as associate editor and review of geophysics and associate editor of the Journal of Climate. He's authored over 200 papers, and we're happy to have him here today.
Thanks, Juan. Thank you, everybody, for joining, whichever time zone you're in. I'm in one that's particularly late at night, about 1 in the morning here in Australia, but I was really keen to join. Didn't really matter the time for me. I just wanted to join in support of this exciting new journal. I'm going to share my screen. So yeah, it's great to join. And as Juan explained, my field in terms of fluid dynamics and fluid mechanics is related to the Earth's climate system. I guess 2 of the biggest bodies of fluid on Earth are the atmosphere and the ocean, and my work's all about understanding the dynamics of these 2 systems, along with the ice that flows off the ice sheets around Greenland and Antarctica, and the interactions between ice, ocean, and atmosphere, how these fluids transport properties around the world. When they do so, how it impacts the planet, heat transfer, energy propagation, the uptake of carbon, and I mean, fluid dynamics underpins all of climate science and all of weather scale, meteorology, and oceanography as well. So it's great to be here. And before I get into some of my science, I just wanted to give a real plug for this journal. We've loved the Journal of Fluid Mechanics for a long time, but I think this new format's very exciting. So I wanted to sort of congratulate the team on putting this together. I look forward to reading articles that come through and appear. And yeah, as I said, as a climate scientist, I'm really pleased to see this, because we can't understand climate change without a deep understanding of the physics of fluid flow in both the ocean and the atmosphere, and of the ice sheets and the interactions between those media. Right down to the weather scale, so timescales of seconds through to timescales of millennia. Basically, we live on a fluid-covered planet, and we're very vulnerable to extremes of weather. We're actually, every day, people are affected by the weather they experience, sometimes in profound and costly ways, with heat waves and extreme flooding events. Here in Australia, it's not long between extreme events. We had a severe flood only a couple of weeks ago in Sydney that did untold damage to the coast, and we're expecting a lot of these extremes to be more prevalent under climate change, but we still are learning some of the dynamics of these systems. You know, the understanding is still quite limited, because our ability to get to the upper reaches of the atmosphere and to the deepest depths of the ocean is fundamentally constrained. We don't have nearly enough measurements of parts of these systems. And the other thing is that the fluids, the ocean and the atmosphere, the scales from millimeters and microseconds right through to global scale, there's a cascade of energy across these length and time scales. And so, and there's nonlinear processes too. So it's a complex interplay of processes over order 10 to the 15 magnitude worth of range of time and space scales, if you like. And so that's why there are plenty of us around the planet trying to understand these 2 systems. And my biggest focus is probably on ocean dynamics. I still see myself more as an oceanographer than an atmospheric scientist. And this animation, the previous animation, was obviously our weather systems observed from space. This is now from a computer model simulation. And you know, the ocean has taken up over 90% of the anthropogenic heat. So as we trap as we trap heat in the system, the oceans are doing an incredible service to the planet by taking up enormous amounts of heat, over 90%. But in doing so, they're changing in ways that are very costly, with rising sea levels and melting ice caps and so on. This particular animation is showing the fluid flow in the abyssal ocean. So this is the densest classes of water we have. I don't know if it's coming through okay across the internet, whether it's clunky or not, but you can see these fast flows in the blues and greens, and you can see filaments of water making their way off the continental shelf where the densest waters formed around Antarctica and making its way into the abyssal ocean. And this is really important because in doing so, it's transporting heat and carbon and nutrients into the bottom of the ocean. This water eventually upwells many hundreds of years later somewhere else. And so it ventilates the ocean, and it renews the ocean of nutrients and carbon and so on. So it's actually critical for the ecology and ecosystems of the oceans, but it's also critical for regulating our climate system. So that's my field, and that's why I'm keen about this journal. I'm going to get out of the animations for a little bit now and show you some work we've been doing recently on global scale ocean atmosphere climate teleconnections. And what I mean by that is I'm referring to ways that the climate system takes a signal from one bit of the planet, maybe say in the North Atlantic here, and through various dynamical processes, creates an anomaly or a change in the climate system, sometimes a far distance away. And in this case, I'm going to go through how the far North Atlantic here can teleconnect to the Antarctic here to the far south. And it can do so over relatively fast timescales. And so I think the range of fields represented in the some 180 participants that have tuned in has got to be very wide. And so I'm sure there are many people who haven't heard of this overturning circulation, but I think quite a few would have. It's been popularized in movies even, this massive overturning of heat in the North Atlantic. And so for those of you who haven't heard of this circulation, there's a flow here into the far North Atlantic. I've unfortunately covered part of this with a title here. It is a transport of heat in the Gulf Stream. Vast amounts of heat move up into the far North Atlantic, and they do so partly because of the wind-driven circulation, but also because in the far North Atlantic, in today's climate, the water is dense enough here in the top left panel here to sink and make its way into the deep and abyssal ocean. And in doing so, more water is drawn northward. It's an overturning circulation that's intimately linked to the deep water flow, dragging this surface water northward. And in doing so, it actually brings a really warm and mild climate to the North Atlantic. And so we're very grateful to this overturning circulation. It's been what we call on and turning over this heat in today's climate right back through the Holocene. You have to go back to the ice ages for when it actually was last, slowed down or off. And so, but there's a lot of concern about this flow because we know that it has been off in past climate states, and all of our projections going forward in the climate change perspective show this circulation to be slowing down. In some simulations, it collapses quite rapidly. In others, it's more gradual, but we're melting vast amounts of fresh water off Greenland. And in doing so, we're going to be slowing down this circulation. There's already good evidence of this and quite possibly collapsing it. And so the question is, what does this do to the climate system? If we are going to collapse this overturning circulation, what kind of changes will we see outside of the Atlantic? And so we did this work with a sort of state-of-the-art global coupled climate model, and it's simple stuff to do. You can switch off, and maybe that's already confronting in itself, the fact that it is simple to switch off the overturning. You basically go to one of these full coupled climate models, and you add some meltwater into the North Atlantic, and that fresh water is less dense, and so pretty much in short time scales, you can cap off the overturning circulation, and that leads to all sorts of changes. And the most obvious changes initially are this cooling in the far North Atlantic. And I put a little icon here for the day after tomorrow, because this is the sort of Hollywood blockbuster that came along, popularizing this overturning circulation and sort of dramatically showing that the shutdown could lead to an ice age within days. And of course, this was science fiction and completely not what happens in the real system. It takes thousands of years to build up ice sheets. But nonetheless, it's true that if you shut down the overturning circulation, you get a dramatic cooling in the North Atlantic. And Juan, by the way, please give me some warning of time, because I'm not quite sure where I'm up to in the 15 to 18 minutes I've got. So if you give me a 5-minute warning, that'd be appreciated. Okay, so this cooling that we get has been documented in many, many papers, but much less understood is the teleconnection that goes beyond the Atlantic Ocean. And so when we slow down the overturning circulation in the North Atlantic, what we do outside of the Atlantic is actually leave a massive new reservoir of heat in the South Atlantic. And so this residual heat accumulates in the South Atlantic. And then what happens, warmer water leads to warmer air, and that is less dense. It convectively moves up into the upper reaches of the atmosphere, as shown in this cartoon here. And so you then get a subsidence, so a descent of air over the East Pacific. And there's a very important circulation in the East Pacific that's due to these El Nino, La Nina cycles called the Walker circulation. And if you start to descend air in the East Pacific here, as I've shown in this diagram, you then get an acceleration. So the trade winds here right across the Pacific Ocean in this simulation then become dramatically stronger. And this whole Walker circulation, this is now altitude on the y-axis and longitude on the x-axis here. So it's a cross-section through the atmosphere going up in height. And you can see this overturning circulation, the Walker circulation, accelerating when we shut down the overturning of North Atlantic deep water. And so we come up with this cartoon diagram. This is under review at Nature Climate Change at the moment, showing that this slowdown of the overturning in the North Atlantic actually triggers changes as far as Antarctica, because once you pile up warmer water in the maritime continent region from these trade winds intensifying, you get what's known as a Rossby wave train. These are waves in the atmosphere that propagate. That they have a dispersion. I'll go into that in a second, but it's basically the warm air here drives an enhanced Hadley cell, which is propagating towards the high latitudes, and that disturbs the atmospheric system such that you get these waves propagating polewards with this arc towards the Amundsen Sea region. And this part of the atmosphere over the last 30 or 40 years has deepened considerably. So this low pressure system here off the Amundsen Sea has deepened considerably. And so we put together this summary of what we found, a global scale teleconnection emanating out of the North Atlantic. And the coincidence of over the last 3 or 4 decades, we've seen each of these bits of the climate system change in this way, but nobody's put this together in a sort of coherent story yet, that the Atlantic overturning circulation there's very strong evidence of a slowdown. We've seen the tropical Atlantic warming, and we've seen an acceleration of these trade winds, and also this deepening of the Amundsen Sea low. And so it's a change in the system driven by climate change, but it's a change that manifests in teleconnections that reach from one hemisphere to the other, right across the tropics, and links really all of the changes originating from the Greenland meltwater entering the North Atlantic Ocean. Okay, Juan, how am I going for time?
Yeah, you've got about 5 minutes left.
Thank you so much. Okay, so in the last 5 minutes, I want to talk a little bit about the Southern Hemisphere, and in particular, I spoke a bit about teleconnections from the tropics to high latitudes. I want to talk to you a little bit about a discovery we just made in the last year or so that we're very excited about, because it leads to a deeper understanding of this pattern of pressure systems you get across the Southern Ocean. And we talk about this as a zonal wave 3 pattern. And what we mean by that is you have typically in any given snapshot of the atmosphere in the Southern Hemisphere is a pattern of 3 high pressure systems and 3 low pressure systems alternating between each other. Now, as you can imagine, these pressure systems are associated with very strong north-south flow. And so you either bring warm air towards Antarctica or cold air moving back northwards. And this huge sea ice decline that occurred in the recent years, so Antarctic sea ice was gradually increasing and confusing climate scientists, although we worked out why that was occurring due to a bunch of processes. But this collapse caught everybody off guard. And it turns out that it actually got to levels that we had never seen in the observed record. So this decline was dramatic. And it was due to this sort of wave number 3 pattern being very, very strong for a couple of months in the Southern Hemisphere. So it actually wasn't like all of Antarctic sea ice declined. It's actually, there were sort of hot spots of decline that coincided with these warm air masses moving towards Antarctica. And so we showed this link in this paper, we showed this link back to the tropical Indian Ocean, but we went into a deeper dive with this to understand the wave 3 pattern, because all of the existing ideas around the wave 3 pattern was that because it's sort of quasi-stationary, it was thought that to be linked to this land ocean geometry. And so with the Southern Hemisphere wave 3 pattern being so strong, the sort of assumption, if you like, was that the fact we have 3 masses of land and 3 bodies of ocean alternating their position around the Southern Hemisphere, that this gave, and the ocean and land surface do have very different interactions with the atmosphere above. And so it's kind of plausible that you might think that the continental configuration gave rise to this 3-wave number pattern. But one of my grad students, Rishabh Goyal, is just about to finish up and submit. He's done a great job with his thesis. And one of the things we set off to do to start with is to sort of build up our planet, if you like, in the model, build up the planet of Earth from a very simple aquaplanet system and, excuse me, progressively add these land masses to see exactly what they did. And we ran 20 different experiments to get to an understanding of the wave 3 pattern. And at the top here is the Fourier filter to pick out the wave number 3 pattern that comes about from each of these simulations. And I'll only show you 3 of these. One is the full aquaplanet. The second is where we just have land masses, as you can see here in the gray, at the mid-latitudes where they occur in the Southern Hemisphere. And the third case is just a single piece of land over South America. It could have been any piece of land over the tropics. It's a fully aquaplanet system in this third case, but we just have a single piece of land here to trigger atmospheric convection. And what we found is that actually the land masses in the Southern Hemisphere really did nothing to generate a wave 3 pattern. So this assumption that had been around for 30 or 40 years was a simple one. It hadn't been tested. It turned out to be wrong. And instead of the wave 3 pattern being there due to land masses, it's convection in the atmosphere. So it's the rising of air over warm water in the tropics that generates this disturbance that propagates poleward. And then once it propagates poleward, at these latitudes, there's a very strong westerly wind jet that propagates from west to east. And the Rossby waves that I spoke about, if you look at their dispersion relationship, they propagate westward. And you get a whole bunch of waves, not just wave 3, you get wave numbers 1 through to 6, 7 in the system. But it's this wave 3 pattern that has a phase propagation going upstream against the dominant atmospheric circulation going the opposite direction that gives you a standing wave 3 pattern. And as we know from the Northern Hemisphere, when you have these standing waves in your jet stream, it can lead to these very extreme weather events over the Northern Hemisphere. And so that's where I should finish up. I had another story that takes us back from the Southern Ocean back to the North Atlantic, but I sense that Juan's been generous with time, and I've probably got to the stage where I should wrap up there. And thank you for tuning in and answer any questions if there are any.
Thanks a lot, Matthew. That was great.
Okay, well, let me start by saying, Matt, a nice talk and particularly nice slides. The bed behind you, I'm surprised you're not in it. It's about 1:30 in the morning. Most impressive. But what I wanted to ask you, what do you think the next big fundamental step forward is to have us understand the climate better?
Yeah, it's a good question, Herbert. I think, I mean, the atmospheric scientists are talking a lot about this convection in the tropics. Our measurements of tropical convection it's a tough thing to measure. It happens on very fast timescales, and as you know, the velocities involved are rapid, and it's tough to get in there and make measurements. And the models we have don't do that physics terribly well. For the ocean, we keep building models with higher resolution, and we don't, as you know from your work, we haven't yet found the limit of kinetic energy in the system. What I mean by that is every time we build more resolution in these models, we haven't saturated kinetic energy. And so it's kind of a boring answer to give, but I think these finer scales that we still haven't tapped into in these simulations, the sub-mesoscale is the next frontier in these models. And one of the areas I'm interested in at the moment is the intrusion of warm water around the Antarctic continent. And down there, the Rossby radius really gets so fine that we need resolution of hundreds of meters. And the typical global models we use for climate projections have resolutions down there of at least 10 kilometers, but typically even more than that. And so to me, it's that age-old answer we've given for a long time. It's those sub-mesoscales that we don't get to with these models.
Matt, very, very interesting presentation. I was just wondering if you could give us a little bit of insight into the types of computer systems, computer hardware that you use for running these simulations, and what's the scale of actually doing simulations of this sort.
Yeah, no, we dominate the use of our national supercomputer here in Australia, and I'm not good on the specs of the computing systems we use. I've got to declare that up front. I chew through the hours, and we have petabytes of data on these systems, but the actual specs I don't have handy. But I think the system we use here in Australia is one of top 20 in the world, top 30 in the world. But you're right, it's a good question, because we do have a huge need for computational resources, and we build models that push the limits of those resources, both in terms of the computational time and the memory processing and the storage they use. So that's been how we get to more resolution. Is not the limit is the computing systems we use. And so at the moment we use millions and millions of hours out of the I think the share, everybody's trying to get on these systems, the microbiologists, the chemists. We're all saying that our computational needs are the most important and need to dominate the machine, but obviously it's a shared platform, and climate, earth, ocean, atmosphere sciences worldwide are chewing through the compute hours to resolve these problems for sure.
Yeah, definitely. I'm sure you can make a good case that your simulations are the most important though, right?
Well, I see medical research is pouncing on these high performance computers as well. And yeah, look, it's a very collegiate field. We're all respectful of the work we're all doing, but for me, looking at how our planet's climate system is going to change, certainly over the next couple of decades, there's big changes in sea level, big changes in heat extremes and so on, and we still are just getting at the beginnings of understanding exactly how that's all going to play out.